Alrighty, hello and good afternoon. We are we are alive. We're also live. Hopefully we stay both for the duration of the afternoon. So yeah, hello and welcome to Thursday edition. Always the Thursdays before a test, I feel like they're a little tenuous because there's the anticipation of the exam opening, mixed with the unknown that it'll bring, and all the good stuff. But at least for one more day, we're not living under an exam. I'm just finding real quick where the problem we left off with. There we go. Okay. That's right, because I knew we had an example that we left off with that we're going to pick up with today. And now I have it pulled up, so let's go ahead and dive in. So, we were, sorry, I'm just gonna rearrange all these cups and whatnot. We were discussing the water ionization constant, right, Kw, and we were talking about. So, just by way of reminder, that is the equilibrium constant for the self-ionization of water when water reacts with itself. And that equilibrium constant, Kw, is equal to the molarity of hydronium times the molarity of hydroxide, and this is equal to 1.00 times 10 to the negative 14th. All right, that is the equilibrium constant for the self-ionization of water. And we were given a problem. I left us with a problem on yesterday. I left us with a problem on yesterday, that asked what is the concentration of hydroxide and hydronium in a solution where there are equal amounts of both, all right? And that is what this example hinges on, the fact that we're dealing with equal amounts of acid and base, of hydronium and hydroxide. All right, what that means is if you have the same amount of each in solution, that literally means that the molarity of one is equal to the molarity of the other. All right, the molarity of one is equal to the molarity of the other, and what that allows us to do then is to substitute in to this equation, solve for one, and then we come back and solve for the other, right? We know that our concentrations are equal. And so as a result, we can substitute into this equation, Kw is equal to H3O plus the concentration of hydronium times, now we're substituting in the concentration of hydronium for the concentration of hydroxide, because we know that the two are equal, all right? So that means that the acid ionization constant, Kw, is equal to the molarity of hydronium squared, all right, raised to the power of 2. To solve for the molarity of hydronium, then we have to take the square root of Kw. So our concentration of hydronium is equal to the square root of the acid ionization constant, which is 1.00 times 10 to the negative 14. All right, when you punch this into your calculators, you're going to get that the concentration of hydronium, when the hydronium concentration and hydroxide concentration are equal to each other, the molarity of hydronium will be 1.00 times 10 to the negative 7. And we know that the concentration of hydroxide will be the same because that was the condition under which we solved this problem. So when the amounts of hydronium and hydroxide in a solution are equal, they'll each have a concentration of 1.00 times 10 to the negative 7 molar. All right. A solution that has equal amounts of hydronium and hydroxide, right, equal amounts of acid and base, has a special name. We say that this is a neutral solution. It is neither considered acidic or basic. It's neutral because even though there's hydronium, which is an acid, and hydroxide, which is a base present, they're both present in equal amounts. So neither is favored. All right. Okay. So again, it's called a neutral solution because it does not favor either acid or base. Now, we've been calculating the concentrations of hydronium, right, for a bunch of different solutions. That was the last batch of problems that we did on Wednesday, yesterday. And they all had a lot of exponents involved, usually, like 10 to the negative, 7, 8, 10 even. These large negative exponents. Well, it turns out that those numbers, those scientific notation, those concentrations in scientific notation can get a little cumbersome to write, and so chemists decided to use a different scale rather than having to write 1.00 times 10 to the negative 14th all the time. That they'd rather deal with integers or numbers with 1 decimal place or 2 decimal place, and that is really the impetus where the pH scale came from. All right, so pH is simply, it's the equation for pH is it is -1 times the logarithm of the concentration of hydronium. All right. I don't know how fresh you are on using logarithms. It's a button on your calculator. It's a function. And this will turn all of those large negative exponents into simple, easy to use numbers. All right. So to calculate the pH, you just take whatever your concentration of hydronium is, hit the log button, multiply by -1, and the pH scale is used to rate how acidic or basic a solution is. All right. So here let's get some practice. Let's get some reps in, kind of applying using this equation to calculate some pHs. I'm just gonna rewrite the equation up here. Totally. Well, it is time to dust that logarithm button off. Is there full form? Okay. Peyton, great question. So what the log function does is, you'll notice if you take the log of 1, or the negative log of, well, here, actually, let's just take 1 times 10 to the third. The logarithm function, if this is 1, and it's got to be 1, the answer, the solution to this function, is whatever your exponent of 10 is, will be your answer. So the logarithm of 10 to the third is 3. The logarithm of 1 times 10 to the 16th, again, is just equal to 16. So it expresses intermolecular forces. So what the logarithm function does is it basically compresses a number. It takes these large exponents of 10 and kind of crunches them down to easy, smaller, bite-sized things. One of the things you'll notice is all of our exponents of 10 are negative. So if you took the log, for example, of 1 times 10 to the negative 9, the answer would come out to be negative 9, and that's why your pH is negative 1 times the log. That way we can deal with positive numbers, because our exponents of 10 that we're dealing with are all negative. Okay. Sorry. Gotcha, Prathana. Sorry, now I understand your question. You're asking if pH is an abbreviation for something. That is a great question. Turns out pH isn't actually short for anything. Math is kind of cool. Yeah, totally. So again, if you just look at this situation, we've got negative 1 times our negative 9, but that makes it a positive when you multiply the whole thing by negative 1. Yeah, totally. I'm so sorry, I didn't understand your question. It's an excellent question. But yeah, it's the p function is a function that just means negative 1 times the log. So this p right here, this p right here just literally means negative 1 times the logarithm of. Okay. All right. So let's get some reps again. For some of us, it's been a while since we've hit this button on our calculators. Let's consider a solution that has we'll put our molarity of hydroxide here, molarity of hydronium here, and then pH here. Potential of hydrogen, power of hydrogen. Those are all great suggestions. It's actually not. It's just P is a mathematical function that isn't found on your calculator. That means -1 times the logarithm of. But those are all those are all actually great ideas for the name. So yeah. But it actually isn't short for anything. So consider a solution where you have your molarity of hydroxide is 1.00 times 10 to the -3rd. All right, the concentration of hydronium here my phone's calculator is not that. Well, you know it's a phone calculator. Oh, hang on. So I'm just punching it into there we go. Scientific. All right, so the concentration of hydronium here would be 1.00 times 10 to the -11th. And your pH, so I'm just going to move our pH over just a little bit. To calculate our pH, you take the concentration of hydronium that is so do most of us. And you just take the log of your concentration of hydronium times -1. So for these two concentrations, our pH here is 11. All right, you punch 1.00, slap that times 10 to the -11 inside the logarithm function, multiplied by -1, it comes out to be 11. If we calculate the pH for a neutral solution, right, one where the concentration of each is -7, the pH comes out to be 7. All right, and let's look at an example where Prathana, great question. Prathana was asking how I calculated the concentration of hydronium, and I did so using the self-ionization of water. Because we know that the ionization constant of water is equal to the concentration of hydronium times the concentration of hydroxide. And finally, let's look at an example where we have a molarity of hydroxide, which is 1.00 times 10 to the -12, and a molarity of hydronium that's 1.00 times 10 to the -2. Totally. Are you giving those? Right. So starting with like the hydroxide is in a problem, but I'm just doing this more for comparison's sake. So this would be the log of 1.00 times 10 to the negative 2, which would come out to be pH of 2. Well, it's the good news. Oh, sorry. The good news, Susan, and to anyone else whose eyes are crossing, is this is not on exam 3, which you're facing tomorrow. This will be on the final, so we've got another 2 weeks to process this, kind of get it under our belts. So that's a bit of good news. All right, now I want you to notice something. So for this one, the example in the middle, this was our neutral solution. All right, this is our neutral solution. There's the same amount of acid and base present in this solution, and it has a pH of 7. All right, that will be true for all neutral solutions. All neutral solutions will have pHs of 7. But you'll notice in the first example that we did, you'll notice that there's, in this example, you have more base than acid. The molarity of the base is higher. Isn't the final next week? Good question. 2 weeks. So in that first example, we have more base than acid, right? A higher concentration. And you'll notice that your pH here is greater than 7. In the second example, when you compare the two molarities, you will see that we have more acid present than base. And when you look at your pH, your pH is less than 7. All right. So the deal is here, when you have pHs that are less than 7, we say that the solution is acidic. And when we have pHs that are greater than 7, we say that the solution is basic. All right? And then pH of 7 is totally neutral. Whoa. Okay, sorry, I'm looking at what everybody is saying, and sorry about the syllabus. And shoot, I thought we had one more week, but tomorrow, next week is the last week of July. So I was wrong about that. I guess we do have a final in about a week. I'll have to look at the syllabus and do some rearranging. Not rearranging, but just, figuring stuff out. So, okay. I will have more information on that in the future, but for now, let's go ahead and keep on rolling with our acid and base stuff. Yeah, sorry, Brianna, for that false hope. Okay, so that is an introduction to pH. For some examples, if you want to see how this could be written into a problem, I'm going to throw these examples out and let you attempt them on your own. You can bring them up in office hours. We can talk about it then. But if you want some practice, and I will be posting, by the way, the Chapter 10 practice homework very soon. But you can check these out. Oh yeah, for so for some fun extra practice, rewatch yesterday's lecture. And in the example problems, for each example, you can change the wording, what is the molarity of hydronium, to what is the pH. The way I'll be testing you on pH is exactly how the exact same types of problems that we were doing yesterday. It's just the last question won't be what is the concentration of hydronium. It'll be what is the pH. All right. So we only have. I was looking at Chapter 10. I'm going to streamline it a little bit, just because we are rapidly running out of time. There are two topics that I want to cover before we exit the chapter. The first is buffers, buffer solutions, and then the second is acid-base titrations. So those will be the last two topics we cover in this chapter. Let's go ahead and start with buffers. So a buffer, starting with what buffers are, might be a good place to begin. A buffer is a solution that contains both a weak acid and its conjugate base. All right, it's a solution that contains both its a weak acid, and its conjugate base. And buffers are resistant to changes in its pH. All right, buffers are resistant to changes in its pH. All right, now let me show you how that is the case. All right, take for example a buffer that contains hydrofluoric acid and its conjugate base, fluoride. All right, a hydrofluoric acid is a weak acid. Fluoride is a weak. It's its conjugate base. It's a weak base. Now, here's how it resists changes in its pH. So we've got this buffer, and let's say we add hydronium. All right. Normally, if you add hydronium, if you add an acid source to a solution, the pH is going to jump up. However, when you add it to this buffer, The hydronium does not directly affect the pH because when you drop it into the solution, it reacts with the conjugate base. All right, the acid donates a proton, so F minus becomes HF, and the hydronium just becomes water. All right, what happens if you add a base to your buffered solution? Again, the base does not get to directly affect the pH of your solution because when you add hydroxide to a buffered solution, it will react with the weak acid. All right? HF will donate its proton to hydroxide, becoming fluoride, and hydroxide will accept the proton from HF, becoming H2O. All right, so the way to think of a buffer is its armor. It's armor against acid and base, because when we added hydronium, the conjugate base fluoride neutralized the acid, and our weak acid, HF, neutralized the base. All right? So that is how a buffer resists changes in its pH. Normally, if you drop hydronium, drop hydroxide in there, it has an immediate effect on your pH. But if you're buffered, there's something in there that will react with the acid that'll neutralize it. There's something in there that will react with the base, neutralizing it. So it resists changes in its pH. All right? So an example that you could run into relating to buffers might look like the following. Write the reaction that occurs when hydronium is added to a buffered solution of acetic acid, sorry, that should be O2, and acetate. All right, so one of the things you have to do when you're solving these problems is you have to identify, okay, we are reacting with an acid, and is that acid what's it going to react with? Which component? And it's obviously an acid, so it will react with the A minus, right, which is the conjugate base. So the reaction that's going to go down will be hydronium reacting with our conjugate base to produce. Now, hydronium is a proton donor, right? The base is a proton acceptor, so the base will accept 1 unit of H plus, becoming acetic acid. And hydronium, after donating H plus, will simply become water. So this is the reaction that takes place when you add acid to this particular buffered solution. All right. Now, to calculate the pH of buffered solutions, we have an equation. This equation is called the Henderson-Hasselback equation. When I was taking Chem 400, I won't say how many years ago, because I think it was like 15 years ago, I had a buddy who called this the David Hasselhoff equation, and it, for whatever reason, that made it more memorable. But the the Henderson-Hasselback equation, excuse me, I still do that sometimes. The reason why I'm telling you this story is if I happen to just start calling it David Hasselhoff, and you're like, what's going on? Now you know. The David Hasselhoff equation is the pH of the buffered solution is equal to the pKa plus the log of our conjugate base, concentration of conjugate base, divided by the concentration of our weak acid. All right, that is the Henderson-Hasselback equation. Let's unpack it for a minute. So A minus, as you know, it's the molarity of the conjugate base, whatever it is. It'll be different for every buffered solution. Concentration of HA, this is the molarity of the weak acid. All right, but something that's a little weird, you may be going, okay, what is this pKa deal? Well, we know pH, right? pH is equal to -1 times the logarithm of the concentration of hydronium, right? So the pKa is actually very similar. It's just -1 times the logarithm of the acid ionization constant, Ka. You'll recall that Ka is just products over reactants, right? So that's all pKa is. It's just negative log of the acid ionization constant. All right. So you'll bump into the problems to deal with the Henderson-Hasselback equation. They're fairly straightforward to solve. They more or less go something like this. What is the pH of a solution with a concentration of acetic acid being equal to 0.500 molar, and the concentration of acetate is equal to 0.350 molar, and the pKa is equal to 4.75. All right. So pH Henderson-Hasselback equation is equal to pKa 4.75 plus the log of conjugate base concentration, 3.50, or 0.350, excuse me, over 0.500. Molarity cancels, which is good. So we take, let's see, 0.35 divided by 0.5, and now we got to do the logarithm, which is where? There we go. Susan, great question. The log in the HH equation does not have a negative sign. And yes, Carolyn, that is correct. And the reason why is because, so remember, we have, Carolyn, this is the acid, and this is the base, the conjugate base. And in the Henderson-Hasselback equation, conjugate base is on top, weak acid is on the bottom. So that's why we put the acid molarity on the bottom and the base molarity up top. All right, so let's see, 0.350 divided by 0.500 is 0.7. We take the logarithm. So this is equal to 4.75 minus 0.155 Totally. All right, so now we have 4.75 minus 1.55, and our last sig vig has to be in the second decimal place. So we get our pH is equal to 4.60 after we round. All right, so that would be the pH for this particular buffered solution. The pH for a buffered solution will always be close to the pH, the pKa of the acid, but it'll adjust up or down depending upon the specific concentrations for the specific concentrations of the conjugate base and conjugate acid. All right, okay. So that is buffered solutions. We have one thing left to discuss, and that is acid-base titrations. Titrations. Okay. Now, there are many types of titration experiments. This is a type of experiment that is not exclusive to acid-base chemistry. However, it's very common in acid-base chemistry to do a titration, and so it's usually introduced in this context. So a titration is a type of experiment. Susan, great question. Susan's wondering if you will get tested on the subjects in the book that we are skipping, and the answer is absolutely not. I will only test you on material that we cover together. Totally. Okay, so in a titration, you use, oh, of course, you use a solution of known concentration to determine an unknown amount of reactant, or it could be an unknown amount of reactant, or it could be an unknown concentration of another solution. All right. So in a titration experiment, you have something where you know the concentration, and you use it to determine either an unknown amount of maybe a reactant or the solution of another, the concentration of another solution that you don't know the concentration of. All right, so here's the basic setup for a titration experiment. So usually in a titration, so you'll use a piece of glassware called a burette. Totally. I totally echo what Kate just said. It is totally okay to be confused the first time you're presented with material. The key is not avoiding it, but diving into it, studying on your own, bringing questions to office hours, reading the book, rewatching lectures, doing everything you need to do to get that material in your head, and repetition and exposure is the key, right? Okay, so you've got this long glass tube called a burette, and there is in the bottom of it something called a stopcock that controls the flow of solution. So the burette is filled up with a solution of known concentration. So, for example, let's say that we have a solution of 1.00 molar sodium hydroxide, for example, filling up our burette. And then, in an Erlenmeyer flask down below, you have a solution, all right? And this solution down here, this is a solution of unknown concentration. Let's say, and you'll measure the volume. So let's say it's It's HCl. All right. Now you'll measure, when you do a titration, you'll measure the volume of HCl you put down there, but you don't know what its concentration is. All right. Now, a couple things of vocabulary. The known concentration, solution of known concentration, this is called your titrant. This is your titrant. And the solution of known concentration, this is your analyte. Sorry, your unknown sample is your, analyte. Your known concentration is your titrant. And then what you do is you open the valve. Well, actually, I should be a little, before I start talking about that, I'm going to scoot this whole thing over. Just a moment. Over the course of the experiment, or we're going to do an experiment, a titration experiment, to determine that concentration of the acid solution, the concentration of your analyte. Now, before you start the experiment, you measure your initial volume, and then you open the stopcock valve to start letting the titrant solution down into the analyte solution, and you usually add some sort of indicator, something that'll change color once the solution becomes neutral, so you know when to stop adding solution. All right, so you add until you see that color change, and you measure your second volume. All right, so you drain down the burette, you drain off the titrant until the reaction's complete, and then your volume of your titrant equals your final volume minus your initial. All right, so you use the volume of titrant delivered in this equation, or in this experiment. All right, so you add titrant till the reaction's done, then you go, okay, we have a reaction here between HCl and NaOH. This is a neutralization reaction. We can write out what the reactants and products of this reaction are. Reactants are HCl and sodium hydroxide. The products will be water plus a salt. All right? And now we can use our volume, our 10 milliliters of acid, together with our molarity and our volume of our titrant to determine the concentration of HCl. Because the molarity of HCl is moles of HCl over volume in liters, right? Well, we have the denominator. To get the numerator, we can use the concentration and volume of sodium hydroxide to then calculate, and then the balanced chemical equation to calculate the moles of HCl. All right, so this is kind of like visual, conceptual, kind of how you would, what this reaction, what this experiment involves. But let's actually get down and do the problem, the example of it. So here's how it would be worded. So 10 milliliters of HCl are titrated with 1.00 molar sodium hydroxide. If 16.68 milliliters of sodium hydroxide are used, what is the molarity of HCl? All right, so again, we need moles of HCl over our volume in liters. We know that we have 10.00 milliliters of HCl. Right, so we have our denominator. Oops. Right, we know what volume goes in our denominator. We need to calculate the moles of HCl using our balanced chemical equation. Yeah, Susan, exactly. This is exactly Lab 10. Lab 10 is a titration lab. So this is one of the cool moments when lab and lecture actually correspond to each other. So to find our moles of HCl, we have to start with the molarity of sodium hydroxide. So it's 1.00 moles of NaOH over liters. And here we multiply by the volume of sodium hydroxide used, right? Of course, we have to convert this to liters. But which we can do. And now we just have moles of sodium hydroxide. Next, we convert from moles of NaOH to moles of HCl. And our balanced chemical equation tells us that this is a 1-to-1 molar ratio. All right, so moles of sodium hydroxide cancel moles of sodium hydroxide, and we are good and ready to crunch our numbers. So we have 1 times 0.01668 times 1 divided by 1 gives us, let's see, 0.0167 moles of HCl. And now we can calculate our molarity because it's moles of HCl over, oops, not 10 milliliters. We got to have our volume in liters. So 0.0167 divided by 0.01 is, our analyte had a molarity of 1.67 molar. All right, so that is a titration experiment. It's one of those things that's actually very reactant focused. You're using a known amount of one reactant to find the concentration of the other solution, the other reactant solution. So it's less focused on the products. I want to issue a caveat emptor. which is Latin for buyers beware. There is a very common mistake with titration experiments that I see all the time. All right. I'm just going to say often, and I even know it's in some of our lab manuals, but often the dilution equation, M1V1 equals M2V2, is, they say, oh, if you're doing titration, use the dilution equation. And I'm here to tell you that you've got to be careful. You've got to be careful for this reason. The dilution equation only works if the analyte and titrant react in a 1-to-1 mole ratio. If they do, the dilution equation totally works, but if it's not a 1-to-1 mole ratio in the balanced chemical equation, then the dilution equation will give you incorrect results. And I want to make a promise to you today. I promise the titrations on the final exam will not have 1-to-1 mole ratios. So if you use the dilution equation on the final exam for the titration problems, you're going to get the wrong answer. Guaranteed. So always you want to approach these problems the way I showed you in this example. Write out the balanced chemical equation and use that to solve your problem. I'm going to write an example up on the board. What about lab quiz 10? That is a great question. And the answer is, I don't remember. I don't know, actually. I don't know if there's a 1-to-1 ratio. I didn't write this one. So it was not written by me, and I mean, I looked at the problems when I imported it into the class, but I don't remember. So, well, hang on, let me write this example up. We won't have time to do it, but you can try it on your own. We can do it together in office hours, etc. But I want to get this one out there. 20.00 milliliters of sulfuric acid are titrated with 0.107 molar potassium hydroxide. The initial volume. Yeah, so here's the thing. Well, here, let me. I see the comments. Let me finish writing out this this question. The initial volume of titrant was 0.10 mils, and the final volume was 22.45 mils. Oops. What is the molarity of sulfuric acid? Okay, so a batch of questions first. I believe, let me just check really quick. I'm pretty sure that the lab, if I remember right, does like an HCl sodium hydroxide titration. Yeah. So the reaction in the lab experiment is a 1-to-1 ratio between titrant and analyte. So in that case, the dilution equation is totally fine to use. Totally fine to use it there. The reason why I bring it up and make it kind of a point of it here is I don't want you to get used to using it as a crutch where you only know how to solve it using the dilution equation, because on the final you won't have a 1-to-1 ratio, so you need to know how to solve it kind of the full metal way. And then so Karenza, your question, does the is the base what gets titrated or the acid? It depends. The analyte is the unknown concentration. The titrant is the known concentration. But either can be an acid or a base. In other words, it changes problem to problem. Alrighty, so okay, so it is 2:30. Let's go ahead and push pause on lecture here, last lecture of our penultimate week. So I will thank you all for coming out. I will see you in office hours in about 30 minutes. Later.